Hi everyone, let's continue on session 1.5. Generalize De Morgan's rules for logic. If P is a propositional function, each pair propositions are logical equivalents. So they are either both true or both false. Okay, so we have two pair of propositions. First one, not for all x p of x. Well, it's equivalent to there exists x, not p of x. Okay, not there exists x, p of x is equivalent to for all x, not p of x. Well, how do we think? Well, it's really like we distribute the not. Do you remember last time we talked about, okay, the not really like the negative? It flip the and an or upside down. So here it is very similar, but it gonna change the for all to there exists. It gonna switch the universal quantifier and the existential quantifiers. So so you can think it like this way. So it's like you distribute the for all, okay? Then the for all x. So the not for all, then it flip it to there exists. Okay, there is this x. X stay there, but for the position, it becomes not p of x. Okay, so here when you break the parentheses, not there exists means for all, x stay there, but when you see a proposition, you put a not in front of it. So not p of x. Let me give you an example, okay? Let's say p of x is people like math. So people X like math. And let D be the students in this class. Okay, then for all X, P of X, what does that mean? Well, this guy means all students in this class like math. I hope this is true. All students in this class like math. Okay, and what is the negation of it? Well, the negation is, remember, all students in this class like math. Well, the negation will be someone in this class does not like math. Okay, the negation won't be like all students in this class don't like math. Actually, it's only some. Okay, so the negation is someone in this class does not like math. Okay, so someone is like there exists. Okay, there's x such as p of x. Now you can see this does not like math, so not p of x. So you can see this is this guy, and it's actually the negation of for all x p of x. So you can see using this example, you can try and understand. Okay, the other pair you can think of there is this x, p of x. So someone in this class like math. What's the negation? So someone like math, the negation will be no one like math. So no one like math means for all students in this class, they don't like math. No one like math, right? So not p. Okay? Do you kind of like understand this De Morgan's laws for logic by this example? Okay, next, let's look at universal quantifier and conjunctions. So suppose there is a propositional function p of x where the domain of disclosure is 1, 2, 3, 4. If we have the statements for all x, p of x, then P of 1, P of 2, P of 3, and P of 4 are all true. i.e., for all x, P of x, which means P of x is true for all x in the disclosure. So P of 1 is true, P of 2 is true, P of 3 is true, and P of 4 is true. So because we require all of them must be true, we have the conjunctions. So P of 1 and P of 2 and P of 3 and P of 4. So this is the relation between universal quantifiers and our logic operators, the conjunctions. So far, so good, everybody. How about existential quantifiers? Existential quantifier, suppose there is a propositional function P of x, where the domain of disclosure is 1, 2, 3, 4. If we have the statements, there is x, P of x, there is x. So some number in the 1, 2, 3, 4 is true. So that's why so it could be P of 1 is true, it could be P of 2 is true, or P of 3 is true, or P of 4 is true. So one of them is true is okay. So that is just to say we have P of 1, or P of 2, or P of 3, or P of 4. So existential quantifier is like disjunction. Okay, so far so good, everybody. Okay. Let's look at more examples. What are the negation of some bird cannot fly? Okay, so here already right now, I already give you the answer here. So let's pretend we don't have the answer here. So some birds cannot fly. So the propositional function is birds can fly, right? Birds flies. Okay, and then cannot is like not P. Okay, some is there is this. So that's why we have there is this x, not P of x. So some birds cannot fly. Okay, how about if what is the negation of that? Okay, negation of that, what, not for all the, not there is this means there for all x, not become, not cancel, so we get for all x, P of x. So it is not the case some birds cannot fly, that means all birds can fly. So every bird can fly, all birds can fly. So far, so good, everybody. Okay, we can do more. How about all birds cannot fly? Okay, so all birds cannot fly. Well, in this case, we have for all x, not P of x, right? The negation will be some birds can fly, right? So negation for all is become the exists, x not become cancel. So we have there's x, P of x. So far so good, everybody. Okay, next we also have some rule of inference about the universal quantifier and the existential quantifier. And here let me explain to you. So for all x, P of x. So which means this guy is true for all x, which means as long as D is in the domain of disclosure, then P of D is true. Okay, so this is called universal instantiation. Okay. Next, if we have P of D for every D in the domain, well, this is then we can say therefore for I forgot to put the 3 dots. Therefore for Lx, P of x. So this is the universal generalization. Okay, next, there is this x, P of x. So that means P is D is true for some D in the domain D, for some D. Okay, so this is called existential instantiation. Okay, next, P of D for some D in the domain D. Therefore, there's x, P of x. This is called existential generalization. Okay, how can we use these rules of inference? So if we're given for every positive integers n squared greater or equal to n, then we can choose any positive integer such as 22, and we can conclude that 22 greater or equal to 22. So here, which rule we're using? Okay, so for every, so we have for all. So this is a universal. We have the for all, and we can just choose a positive integer. So this is universal instantiation. Universal instantiation. All right. Okay. Let's continue. Consider the argument, write it symbolically. For every real number x, if x is an integer, if x is an integer, then x is a rational number. Okay. The number square root of 2 is not a rational number, therefore square root of 2 is not an integer. Okay, so yeah, I'll also put down the answer here. Okay, so let p of x be x is an integer, and let q of x be x is a rational number. Okay, then for every real number x, so for every x in R real numbers, if x is an integer, so p of x, then so implies q of x. So the first sentence gives us this guy. And then the number square root of 2 is not a rational number. So this gives us not q of square root of 2. Okay, therefore square root of 2 is not integer. So we have therefore not p of square root of 2. Okay, so let's prove. So this is the argument. Let's prove it. So let's number it. When we're asked to prove some arguments, we're gonna number the lines, and we're gonna, so 1 is that, 2 is that, then 3 is what we get. So for all x in R, p of x implies q of x. Okay, so here, because square root of 2 is in R, so then we have p of square root of 2 implies q of square root of 2. And this is from line number 1. And what rule we are using? We are using universal instantiation. Universal instantiation. Okay, so far so good. Next, we have not q of square root of 2. So, wow. Do you remember, like, p square root of 2 implies q square root of 2? The contrapositive is not q of square root of 2 implies not p of square root of 2. And because we have not q square root of 2, so actually we can conclude not p of square root of 2. And this is from line number 2 and 3. And we are using Models tolerance. Okay, so actually Models tolerance is the same as you first consider the contrapositive, and then you use Models tolerance. So it's like two steps you combine together, you get Models tolerance. So far so good, everybody. So we can actually show it. Okay, so here are some tips for you. First, to prove that the universally quantified statement for all x, p of x is true, you gotta show it for all x in the domain of disclosure that the proposition is true. Showing that the statement is true for a particular value proves nothing. Okay, so 1 or 2 values you cannot prove for all. So for all, you really need to to show the statement is true for all x in the domain of disclosure. Only one or two values is not enough. Okay? Next, to prove the existential quantifier statement is true, well, you only need to find one value in the domain of disclosure that make it true. Okay? So because there exists, if you can find one value, then you have shown there exists some number such that this is true. Okay. Next, to prove a universally quantified statement is false, you actually need to find one value to show it is false. Okay? So you only need to find a counterexample. Okay, so to show it does not work for all, so you find you show that it does not work for some. Okay, then you can show it is false. Next, to prove an existential quantified statement is false, you must show it is false for every x in the domain of disclosure. Showing it is false for a particular value does not prove it's false. Okay, you have to show. So you want to show no one worked. No value works. Okay, now then you have to show for all of the values in the domain of disclosure, the propositions cannot be satisfied. The proposition function is false. Okay. Yeah, so be careful with that. And that is session 1.5. We will continue next class. Have a nice day. Bye.